That's a lot of chat messages already. Anyway, welcome to the second meeting of ENGR 1330. And I actually want to kind of congratulate you all collectively as a class. I went onto the Blackboard server thinking it would be easy for me. Well, I'll grade the 8 or 10 lab ones that were turned in, and there were about 68 of them. It took me an hour. It's not hard to grade because that was a fairly straightforward lab. But anyway, congratulations to you all collectively as a class. That's a huge relief off of my mind. At least 70 of the 90 pretty much are on top of all that. And a few folks went ahead and took the quiz, and that's fine. Any time I create a quiz, I'm just going to post it immediately. It'll have a due date. But if you see one appear and you haven't done it, take the quiz. I mean, if you feel like it. If it seems like a topic that you're not ready yet, then you can wait. And I'm stalling a little bit. See if I have the recorder on. Am I actually recording? What I was doing when you all were... Looks like I'm recording. That's odd. Usually I'm low on disk space on this computer, so I was tidying up, which means, just deleting files and hoping they're not important. And that is the nature of our modern lives. We'll get started with the course formally. Grace, yeah, the quiz is in either lesson 2 or lab 2. Oh, yeah, never mind. I'm responding at slightly slower speed than the rest of you all can collectively. Okay, so let me get to today's stuff. Get my Firefox up and running. I hope this doesn't break the connection. Yeah, it didn't. Wrong guy. Firefox. And get that thing minimized. I want to go to Blackboard. And with any luck, it set the cookies. No luck. All right. Put my charming face over here. Bring up the chat window. Stick it here. I think I can get this thing to, gotta get this to change shape. Oh, that'll work too. There we go. So everything on the screen is getting captured. And the main limitation is when I run out of disk space and it won't tell me. And no longer joinable. Oh, the GroupMe is no longer joinable. All right. So today we're into the second lesson, lesson 2. And this particular lesson is a little more in line with probably the expectations of an introduction to programming. I'm going to do a quick experiment. I put a link here to a copy of Lesson 2, which will exit the Blackboard server. And cool. So this is the same thing that should be on the Blackboard server. I'll do that with everything as I get them built. These links are to a different machine. For me as your instructor, the reason I'm doing that is it's trivial for me on this new machine to switch over to a functioning Jupyter Notebook environment. So the lesson for today is an introduction to the concepts of computational thinking, and then a beginning of a review of some important components of the Python programming as a language. And actually a lot of this stuff, it doesn't matter if it's Python. You could substitute the word Fortran or C or even C++ for Python. Those languages are not at all exactly alike, but there's a lot of commonality, namely because the machines are kind of all the same thing. So we'll review concepts of computational thinking, which is the title of the course, and then we'll look at some important beginning features of Python. And if you're already comfortable with it, just follow along, and this will be review. So the objective of this particular method is, well, it says understand the concept of computational thinking. That's hardly an objective. The objective is to introduce the concept of computational thinking. And then the second objective is to introduce and demonstrate Python variables, data pipes, types, and operators in programming. So computational thinking refers to the thought processes involved in expressing solutions as computational steps or algorithms that can be carried out by a computer. So these references here, Cooney, Snyder, and Wing, 2010, and Aho, 2011, Lee, 2016, are recent references on this computational thinking. This is being sold as if it's a new concept. Computational thinking is just new words for old ways of problem solving, and I find it kind of ironic. I have the advantage of being an old dude, so I can see the parallels. There's actually a 2005-2006 paper. I can't remember the author's name. She was a graduate student at the time. She had a really interesting paper, which is The Problem with Computational Thinking. And it was very controversial, and it's unfindable now. The links to it have been, every time you run it down, it comes up as a 404 error. So finding the archived paper is unfindable. She is now a professor somewhere on the East Coast, all into computational thinking, so maybe she took it down as a matter of business survival. And to contrast this computational thinking with programming, and actually I would take this definition of programming is, in my opinion, incorrect. So what the author of this slide says, programming is writing code in a specific programming language to address a certain problem. That's not exactly right. That's coding. They've just described coding. Programming is designing a recipe to address a specific problem, and then coding is the next step. Now, computational thinking is an approach to solve problems and actually develop these recipes. A good example that I can come up with is you've all been exposed to the scientific method. Hopefully you survived it and got immunized by it. But it had essentially a 5-step process, which was to observe a phenomenon, hypothesize a cause to that phenomenon, design an experiment to test the hypothesis, conduct the experiment, interpret the results, and then redesign the experiment, basically confirm or refute the hypothesis. That's computational thinking, but that's called the scientific method. It's a systematic approach to break observations of phenomenon in the world into pieces that we can examine, and using those pieces come up with an opinion or even a testable experiment to understand how things work. So that's computational thinking from a scientific method perspective. In its more conventional sense, the CT approach is to break down a problem into smaller parts, look for patterns in the problems or in the smaller parts. And so the pattern recognition is important. That's a fancy way of saying don't reinvent a wheel. So if it looks like a wheel and you already have a way to deal with wheels, try to adapt the way you already have to deal with wheels to your new case. Find out what information is required. So in the scientific method, that is design an experiment to test the hypothesis, and then develop a step-by-step solution. That would be conducting the experiment, or an algorithm that would be developing the recipe to obtain the solution. And the 4 pillars of CT are listed here in this diagram. So here they're just shown as 4 blocks. So imagine you are a seagull flying over this flag of Finland, actually. I think that's Finnish. Huh. I'm sure they never intended that to look like a flag. So decomposition is holding up one corner of the building, pattern recognition is another, algorithms is another, and abstraction is the 4th, labeled 3rd here. So the pillars are decomposition, pattern recognition, abstraction, and algorithms. We'll kind of discuss these as we go in turn. Abstraction, I'm jumping ahead to 3, is to simplify the real situation that we're trying to explain into an abstraction or approximation of the real problem. Modern jet aircraft can fly with very little human intervention. I have a nephew who's a commercial airline pilot. Actually, he's not right now. He's sitting on his butt waiting to get his job back. But him and his co-pilot, when they would go drive the plane from San Francisco to Japan, because that was his usual route, they turn the thing on, flip switches, but pretty much boot up the aircraft. They enter a few command codes in, and then they can sit back and twiddle their thumbs for 9 hours. The plane will pretty much fly itself. It could even land itself. The abstraction to do that's encoded in the computer programs that fly the airplane. I mean, there's millions of real influences on a real aircraft. The designers have abstracted it to a handful of necessary ones. And that's what's meant by abstraction. So maybe the necessary ones are some wind speed input, and let me admit the new victim. There we go. Our wind speed input, what the current attitude is, outside air temperature, fuel remaining, and then fuel burn. I'm making this stuff up. I haven't played Microsoft Flight Simulator in a while. But anyway, you maybe down to 85 or 90 different inputs are necessary to fly a huge aircraft and not have it hit the earth too hard. And that's the abstraction aspect. Pattern recognition is recognizing similarities between two seemingly dissimilar processes. Decomposition is breaking that airplane flight down into those 90 different input components that need to be managed. And then the algorithm is the control programs. So now we'll look at the definitions of our colleagues. So decomposition is the process of taking a complex problem and breaking it into more manageable subproblems. And so here's a couple of examples. The first one is writing a paper. Actually, it should be formatting a paper. In this case, the paper itself is the high-level object, and it can be formatted or broken into 3 parts: the introduction, the body, and the conclusion. And then for each of those parts, we go out to the internet and download various copies of introductions, bodies, and conclusions, smash it all together, make a few changes so we can claim it as our own and submit it. No, I was just kidding right there. That would I'd probably get it done on time, but it wouldn't be a very effective way of writing a paper that's really your paper. So that's the format. Another example is a panoramic image. You may have done it on your phone or camera. What you do as an operator is you point the camera and then you kind of sweep it across the horizon, and it'll build this panorama. What's happening inside the machine is it's taking a whole bunch of still images, and then it overlaps them edge to edge, removes the duplicate common features and replaces it with just the single common feature, and stitches them together. That all happens inside. But the decomposition is multiple photos, geographically overlapping them, and then stitching them into a single image. Pattern recognition is another important component of CT, and in this we want to find similarities or shared characteristics of a problem. That's the this is the don't reinvent a wheel component, and by far it's probably the most important component in practical programming or problem solving that there is, and you'll find it throughout the rest of your, I guess, college and working career. You will at some point in internships, depending on which discipline in engineering you're in, but there's always this thing, well, do you have a go-by for that? Essentially, do you have a template that I can follow? Is there a pattern that's been recognized that I can follow to solve a problem? And those are huge. And most businesses have such things. If they don't, that means they're a new business, like a startup, or they're about to go out of business, like a failure. Okay, we use the example here. So finding similarities or shared characteristics of a problem, and that makes the problem easier to solve because we can apply a solution to one part of the problem and then reapply it to each occurrence of the pattern. So as an example that the slide developer has is uploading an album of photos to Facebook. And the pattern is photo, or I guess the object's a photo, and there's different photos. Each one has metadata, never metadata I didn't like, which describes the photo. It's not necessarily the data that's in the photo, but it describes the photo. Then that gets the data in the photo goes under compression, and the metadata gets put to a data server. We're going to learn about something called a Python dictionary, and this is sort of an example for that. The metadata provides the keys to the photo, and then the actual data is the compressed photo. And actually, while I'm on this slide, this idea of metadata is huge. And so in my career, metadata it probably was always there, but it came along the way for me a few years ago. And one of the issues in some engineering work is that people will often send a file to other people, I mean legitimate business use, but all they're really doing is setting the metadata, and the metadata normally contains pointers. Metadata has things like what host machine is the actual file located on, and what various settings of the program to look at the file are. And if you send it to somebody else halfway across the country and they don't have access to that machine, then metadata is useless to them. And that's something to keep in mind in other classes. It shouldn't make much of a difference in this one. The next is abstraction. And here we want to determine important characteristics of the problem and filter out the ones that are not important. And these are characteristics that are used to create a representation of what we're trying to solve. This data representation, abstraction, and filtering are a huge component of building the data model. And you can think of the data model as just the collection of data that are relevant for the problem. Data model, database, data file, they're all somewhat conceptually interchangeable. So here's two examples. Imagine a bunch of students in university like yourself. Things that are important are the student's name. It's funny how the billing address comes up. Yeah, student's name, student's money, phone number, and your student ID number, your R number. Those are pretty relevant for operating a university. They're relevant to me as an instructor. For instance, for all of y'all listening right now, your name and your ID and your email are kind of important because that's how we communicate in this class. The phone number and billing address are not terribly important for the class, but they're in the same database I have access to, and if for some reason I need to get that, I can. I don't have much need to know your favorite color or food preferences or shoe size. And I'm not asking you to put that in chat. At this instant in time, I don't really care. But that's what's meant by the abstraction. Identify the relevant and the non-relevant components of information that you have. Now, who do you think does care about your favorite color, food preferences, and food size? Absolute silence. No one. My mom. Ad company. Whoever said ad companies. Yeah, that's what I was going for. The FBI doesn't care. They just care about who you're seeing. Google, Facebook. Google. Yeah, okay, you got it. You guys got the point. Excellent. Moving to books in an online bookstore. The FBI doesn't need to know. They already know. That's funny. Actually, the FBI probably doesn't know, but the Russian Federation does. Moving on to another example, books in an online bookstore. I'm assuming these are electronic books. The title of the book, the ISBN number, which is like a key that identifies the book in the Library of Congress, the authors, the category, and maybe an abstract matters. What's not important from the standpoint of operating a bookstore is the cover color, which okay, I'll quit making smart aleck Russian comments. It's actually kind of a family joke, because when my wife forgets her password, I say, call Vladimir Putin. He knows somebody that knows it. And we have a good laugh and then move on with our lives. So the cover color, the author's hometown, the complete content, I'm not sure what that means, because it seems like the complete content is the whole point of the book. But certainly the cover color, the author's hometown, are not terribly important to operating an online bookstore. They might be important to the marketing part, but not the actual finding and delivering of the online book. So that's the abstraction step. Algorithms are the actual, they're the actual recipe that gets things done. So here they're presented as step-by-step instructions of how to solve a problem. That's actually a pretty accurate description. An algorithm specifies what's to be done and the order in which it is to be done. So here's an algorithm for making a cup of tea. Let's see if this is how I do it. Okay, so the first item in the algorithm says fill electric kettle. Now, one weakness of it doesn't tell us what to fill it with. We're going to presume water, and if we don't have an electric kettle, we have to modify the algorithm, and we'll look at conditional computation actually today in lab, and that would be the computational equivalent of how to subdivide this algorithm. So this one is not quite yet step by step, but we're going to go with the example anyway. The second thing is to boil it. I don't know if boil the kettle, boil the water. So again, the reason I'm being critical like that is when we're teaching this to a microprocessor or a computing device, as smart as we think they are, we actually have to get down to real intricate detail so that the process is understandable and process is communicated to the machine. So boil the water in the electric kettle, item 2. And then item 3, pour the hot water into a cup. So if we went to the trouble to fill the electric kettle, we probably should have had obtain a cup. Item 4, place tea bag in the cup. Item 5, wait for 3 minutes. Item 6, remove the tea bag. And there should be a few more items. At the point of removing the tea bag, the cup now contains tea. The tea bag is now waste, which has to be disposed of. And at some point, we get to drink the tea. So the humanly simple act of making a cup of tea, which we can do pretty much without thinking about it, you can do it half asleep, when decomposed to its component parts is actually a reasonably elaborate recipe. And I chose that word recipe not willy-nilly. You can substitute the word recipe for algorithm in most computing contexts, and it'll be correct. So if you want to remember what an algorithm is, it's a recipe to get from raw materials to a final product. And the raw materials being various inputs, and the final product being an answer to the question you're asking. So here's a case study using meeting scheduling as an example. So we have a desire to schedule a meeting. The decomposition is that scheduling a meeting is at least 2 steps. So perhaps there's an earlier meeting request and we need to check and remove conflicts. Then there's a pattern matching step, which is to examine unscheduled requests and choose the one that best fits the meeting attendees. And you all may have perhaps participated in that. A common way that's done that I've been part of is doodle polls. There's like 75 people and they give you a whole bunch of possible meeting times, and you have to click the ones that are best for you, submit it back to the server, and it magically picks the worst of the times that you selected you could be available. But that's just life. And then abstraction, each request is presented with a proposed start time, end time, and a name for the meeting. And then the algorithm is to go through all these requests, find the earliest available one, generate the schedule message, and then look at other requests and remove it if overlapped with scheduled ones. So those are an example of the 4 components of computational thinking. Now moving on to the programming aspect, in Python, for instance, which is what the subject of this class is, the program, what we call a computer program, or what I will refer to often as a script, is the realization of an algorithm that uses a syntax or a set of instructions that the computer can understand. And we've pretty anthropomorphized this "can understand." Computers have instruction sets that are built into them by the manufacturer, and to create a program that can be fed into the processing units or GPU or CPU, perform their operations, and get out the other end without the thing screeching to a halt is what's meant by syntax it can understand. There's only a few hundred of those instruction sets. I'll dig up an example in a future meeting of what's some assembly language from an old control data computer that I programmed in the 70s. The instructions themselves are kind of cryptic looking, but they don't do much. There's a fetch and a put and then a push and a pop, and you add stuff, and that's about all there is to it. It's a very limited instruction set, but you can do a lot as you string things together. The algorithm is the recipe, in this context, to manipulate the data. And there's a couple different ways that data is conceptualized. One is a procedure-oriented programmatic method where the data is operated on. The data itself is not changed. Operations performed and different things are created. And then the other more modern one is an object-oriented structure where the data become parts of objects and the objects get manipulated. It's mostly semantics, but there are some fundamental differences in the way those two worlds are managed. The data itself is stored somewhere. It says stored in memory, and then the program accesses that data in memory using its address. I'd say that's mostly correct. Your computers have 4 or 5 different memory locations. There's a couple of cached memories that are computationally or time-wise close to the processing unit, and then you have intermediate memory, and then you have disk space, which is relatively slow, not in human terms, but in computing terms. Each of those has an address, or think of it as a post box that has a code on it so you can find out what's in the memory. And then a variable is a way of naming a memory address. So memory addresses are, if we look at them in hexadecimal or odd looking things, like 08, 08, A3, F2, like 36 or 60 characters represent that address. That's pretty hard for us human beings to keep track of. So what we have is we declare them to be a variable. We make an association. So that funny address, I'm now going to call it Fred. So I have to refer to Fred instead of referring to this cryptic address. And that's a lot of what these programming languages do for us. So they give us a convenient way to access different parts of the memory space. So here is an example from the human side of the picture. On the left column you see, so this is an example of variables. And things to keep in mind: a variable is a name for a piece piece of data. No, a variable is a name for a location in memory. The contents of the variable are the data. The value can change during execution of a program. So a variable means that there's a name associated with a memory location, and the contents of that memory location are permitted to change as the program proceeds. We define a variable by its name and an initial value, and then the concept of assignment is done with the equal sign, where we push a value into the variable. So this word define is somewhat important, not in Python, but if you have an occasion to have to deal with older languages, you'll be able to understand the code fairly quickly, because normally there's a variable definition component where they're explicitly defined before anything gets put in them. And the Python scripting language we'll be using in this class kind of simplifies that, in that if you just type a variable name and set it equal to something, that'll create the variable. So here's an example. Here's a variable whose name is values, and the contents of values. So we have this square bracket, and we'll learn more about that soon, are 150, 40, 70, 90, 10, 12, 8, and 112. Another variable named target. The contents of target are the single value 12, and a variable named count, whose single value is 0. So let's return to the first line. Values here, as this is constructed, is a variable type called a list. So the variable name is value, and the contents are these items here in the list. And the way to refer to a particular item is the first item in the list has an index or an identification code of 0. The second item in the list is has 1. Third item on the list is 2, and so on. So if we were to type the expression values square bracket 7 close square bracket and have it print that, it would go 0, 1, 2, 3, 4, 5, 6, 7. It would print the value 8 to the screen. Lists are actually super important, and we'll spend some more time on it. Now, target is a single valued variable, so in a mathematics context that we call a scalar. And the way target is assigned right here, anytime we print the contents of target, we'll get a 12 back. Count, same thing, except that count is now used in a repetition sequence here, and its value changes. And so this bracket right there, where it says count equals count plus 1, as it's executing through this controlled repetition process, this particular expression says, take the contents of count, let's assume right now it's 0, add 1 to it, 0 plus 1 is 1, place that result back into count. So one pass through this expression, count will change value from 0 to 1. This structure here in line 6 of this particular script, that structure is incredibly common in all computation. So taking a value of a variable, self equals self plus 1, is extremely common. It's actually so common there's a special operator to replace that and make it a little bit easier. So some ideas about variables. You want to give them meaningful names, not because the computer cares, but presumably you might have to maintain this program. And so that doesn't sound like much until you build a program or you've used a program for a couple years, and then something breaks or there's some change, and you have to go back into the source code and maintain the program. 2 years is plenty of time to forget a whole bunch of stuff. And so you would be spending a lot of time in maintenance just trying to figure out what the program was supposed to do again. If you give variables that have I'll answer your statement, Travis. That's actually pretty good. If you just give variables like variable 1, variable 2, and name them stupid things like that, you'll never be you'll be able to figure out what it does, but you're creating a problem for yourself. So when you can, you want to make the names meaningful. The other convention is that variables should not include uppercase letters. I am a huge violator of that, but it's a Python convention to keep them all lowercase. Now let's look at all these variables. 2 of them, which are in boldface, are not don't follow the naming rules. So these are the naming rules. The variables can consist of letters, digits, and underscores, but they cannot start with a digit, and they cannot start with a special character. Okay, so exchange underscore rate, that's a legitimate variable as far as Python's concerned. My underscore name is also legitimate. Is underscore student is a legitimate variable name. Name, all lowercase letters, is a variable name. In fact, this could all be all uppercase and it would still be a legitimate variable, but it would violate a programmer's convention. My underscore name is legitimate. Now here's the first bad one, $ underscore class. The problem here is the leading $, and then one class, the leading one, makes those non-Python variables. Okay, so it looks like Farang took care of my question. Yeah, as he answered in the, unless you explicitly tell it otherwise, Python will do a typecasting based on what's assigned to a variable. So if you assign a integer like a 1 or a 2 or a 3, the variable defaults to being an integer. Actually, we have some exercises. I think they're today. We'll learn that more. Java and C, you often actually want to pre-allocate variables, and that will that's just a different. So we asking Java or JavaScript? So yeah, I think the statement was about Java. Yeah, because JavaScript, which is a scripting language that works in HTML files, that's pretty Python-like. You can get away without explicit variable definition, but it's also a good way to create things that you can't maintain. So we've gone through this slide and identify the 2 that are non-variables. There's a set of keywords in the program language that you can't use for variable names, and the interpreter will usually catch them if you attempt to use them, and it will throw an exception, which is jargon for saying it creates an error, and the interpreter stops running, gives you an error message, and waits for you to repair it. And here's a list of them. And you know, if you want to use a word like this, that's fine. That's the beauty of the underscore. You can either prefix it with underscore, or you have global underscore mine, or my underscore global, and you can still use the word if the word has some importance to you in future program maintenance. It's usually easy enough to work around any of it. I mean, that's not a huge list. And then we're going to go through the different types of data that are represented. So the first, just by order how it usually appears, is an integer. So integer data are numeric, they can be positive, negative, or 0. They have no fractional component. So 2045, 767, 0, minus 87, minus 435. That representation there is integer. The reason there's a distinction between integer and the next one, floating point numbers, is the way arithmetic is performed. If all parts of an expression are integer arithmetic is infinite precision and extremely fast. I mean, subtraction, for instance, is done by something called ones complement. You take the integer number, you convert it to binary, you flip the sign bit, you add it to the next number, and you've just created a subtraction. And when you convert it back to decimal, you've done subtraction. And that's, at assembly level, that's like nine steps. It's very fast. With floating point, we have a decimal point, or it has a fractional component. Floating point arithmetic is quite a bit slower because you have to keep track of where that decimal point is as you perform arithmetic. Examples here: 1433.3, 140.75, minus 25.187, minus 100.1, or one that's not displayed. So if you had a picture there of 32 point, that decimal point turns it into a floating point number. We'll do examples of that in lab also. Mixed mode arithmetic, default, at least our interpreter, if any member of the expression is a floating point, the arithmetic is done as floating point. Automatically, you don't actually have to tell it. Other older languages, you actually have to do the type conversion explicitly. In one way, you could say that's kind of a cool thing about Python because there's no thinking required. The other way is it enables you to make arithmetic mistakes that later on can be kind of hard to detect. I mean, the program will run, but it'll produce slightly wrong numbers, and it can take weeks to figure out what's going on. The next variable type is a string, or alphanumeric. And that's a collection of one or more characters. It says enclosed in single or double quotes. So the single or double quotes is a delimiter that identifies that everything between those is a string literal. So double quote, computational thinking with data science, end double quote. The string variable is computational thinking with data science. The quotes are not part of the string variable. And there's some tricks that you have to employ when you do need to keep single and double parentheses. Now, an important thing about strings to remember is that the character the characters 0 through 9 are characters. So we can... Someone needs to be muted. It's just temporary. You can unmute yourselves if you have to ask a question. There we go. Apologize for that. It was screwing up my way of thinking. Okay, back to string. So the numerals 0 through 9 are characters, and so they can be part of a string variable, and that at times can be a little confusing. When we use the built-in function called input, which will take input from the console, whatever when you type it in, the Python 2.7 used a function called raw_input, and that took whatever came in, and it was a string, and then you had to explicitly convert it. So the Python 3 uses the keyword input. They took the word raw off. It pretty much does the same thing. Any variable that comes in through the input function is first treated as a string, and then to convert it into numeric, you have to explicitly do that. And we have a, we'll show that in the lab, how to do that. There's one other type, a Boolean or a logical variable, and that's a variable that takes on a value of true or false, or more specifically, a value of 0 or plus 5 volts. Boolean or logical are the keywords for the different variable types. And then there's the advanced data types. These aren't really data types. These advanced things are structures, because an array, a list, a tuple, a set in a dictionary can be either an array of integers, an array of floats, an array of strings, or a list of integer float string Boolean, or a dictionary of integer float string Boolean, or mixed of them. So the types are these 4 types: integer, float, string, Boolean. The structures are arrays, lists, tuples, set, dictionary. And we already saw a list earlier, back up here, somewhere back up here. So this is a list. It's a list of integers. There we go. And then when you're writing our scripts, we sometimes want to leave messages or comments to ourselves. Let's see what it says. Information to help readers understand the source code helps them. That's one use of them. A lot of times we'll leave messages to ourselves. It'll say something like change from range 1 to 11, range 3 to 11, rerun, see what happens. But anyway, the hashtag symbol identifies everything on that line of a script file onward as a comment. And for example, in this structure right here, where it says for I in range 1 to 11, colon, right after the colon, if you wanted to, you could put a hashtag in a comment, and it gets interpreted as a comment, and the preceding part is treated as code. I'll show you what I mean when we get to lab. Our next topic is operations. So these are called unitary operators, or think of them as arithmetic operators, and they perform the indicated arithmetic. So here we have a variable named num1 and num2. The contents of num1 are 15. The contents of num2 are 2. And here's a this word here is called an expression. It shouldn't be operation. Here's some expressions, and here's what would happen. So this first expression, sum equals num1 plus num2, that is, into the variable named sum, place the result of the integer number 1 added to the integer number 2. The arithmetic operator plus is addition, and the result is 17. Now, if num1 and num2 happen to be string variables, this operator plus doesn't do formal addition. It does an operation called concatenation, which means it joins the first string to the second string. And we'll see that later on too. This next one, the diff variable takes on the contents of number 1 minus number 2. The operator is the minus sign. There's numerical result. Product is num1 shift 8 number 2, and that's the multiplication operator. And here's a tricky one. Here's quotient, number 1 divided by number 2. If it's a single divide by default, it's going to do floating point division, whether number 1 or number 2 are integers or not. If we do the next one, integer quotient, with the double divide sign, then that does integer division. And so integer division divides the first number by the second number. gets the quotient, and then there's a remainder term that's tossed away. So if you divide, well, here we go, 15 by 2 in floating point would be 7.5. In integer, it drops off the remainder of the half. And then the next one is exponentiation, or power. Number 1 to the power number 2 is the double multiply sign. And that, if you're come from an Excel world, you're used to the caret sign or the up arrow sign to perform exponentiation. Interestingly enough, there's only a handful of scripting languages that actually preserve that. So original Fortran was double exponentiation. Original C was this double multiply sign. The R scripting language, which is actually kind of built in Python, is this double exponentiation. If you want a special sign, you actually can program that. I'm not even going to tell you how, because it would take me a week to remember how. The last operation here is called the modulus, or think of it as the remainder function. So it takes number 1, it divides it by number 2, performs the integer division, and then returns the remainder. So the number 1 is 15. If we divide it by 2, that's 7. So 7 times 2 is 14 with a remainder of 1, so it returns the remainder 1. The modulus function has a lot of interesting uses. It gets used a lot in count-controlled repetition as a way of, have I done something enough times, maybe I should do some output. And as it becomes appropriate, we'll look at that in labs. There's a computational preference, or precedence, in the order that it performs computation. And so the way it works is, the first thing it will do in evaluating an expression is it will evaluate everything that's in groups, in parentheses. Then within that, it performs exponentiation, then multiplication, division, modulo, and finally addition, subtraction. So you can kind of remember these as MDAS. So it's parentheses, exponentiation, multiplication, addition, division, addition, subtraction. One way to simplify life is to make use of parentheses as much as possible. So here's an example. We have C is equal to square root of a squared. This has got to be square root of a squared plus b squared. The radical didn't render correctly. So if we do the following, C equals a times a plus b times b raised to the half power. Well, this first one's a squared. This is the square root of b times b, so this part's b root b. So this is a squared plus b root b, which is not the square root of a squared plus b squared. This one is a squared plus b squared raised to the 1/2 power. That would indeed give us the square root of a squared plus b squared. And the one right below it, group a squared plus group b squared. The entire group raised to the 1/2 power is also the square root of a squared plus b squared. So given the first one, the first line is absolutely wrong. But the next two, 2 and 3, actually produce the same result. The question is, okay, so Lance says, is there a difference between 2 and 3? That's what I'm trying to explain. 2 and 3, as far as the machine are concerned, will produce the same result. As far as a human being is concerned, 3 is a whole lot easier to maintain, because you can clearly see that A is multiplied by itself, and that result is one component. B is multiplied by itself. That's another component. Those two components are added to one another, and then they're raised to the 1/2 power. So if it was me, this would be, in my opinion, that would be the way I would code something, because a year from now I could go back and look at it and immediately know what the grouping is. And that's the use of the parentheses. I'm tempted to go do an example of why that might be important, not in Python, but trying to think if I don't want to waste the time. I have some online code that I could show you why that grouping is important. Essentially, when our arithmetic is complicated, in other words, maybe there's like 17 items to the right-hand side of that equal sign that have to be evaluated. At that point, grouping becomes absolutely vital. So our next set of operations are the logical operations. So these are called comparators, and they're listed here. So the double equal sign is logical equal to. So the way to interpret that, or I interpret that, is that A is identically equal to B. So by identical, the only thing that's different between the two are the names. The contents of A have to be bitwise identical to the contents of B, and they have to be the same variable type. The exclamation point equal sign is the negation of that. So A is not equal to B. Greater than equal, less than or equal are fairly self-evident. And if we execute those particular expressions, the result is returned as true or false. So you can think of that as we're making an assertion in the code. We assert A equals to B, and we want to know if that's true. Is the assertion true? If it is true, we get a true back. If it's false, we get a false back. And then the results of those can be used for program flow control. Then the last part, and then we'll, I'll get a sip of something to drink because my voice is getting raw, and we will prepare to segue over to the lab. There's two built-in functions that we're going to find kind of useful. One is the input function. The other one's the print function. So what the input function does is it's going to take input from standard input-output, which in the case of our Jupyter notebooks is going to be it's going to generate a notebook input cell for us. We'll do an example to illustrate that. And then anything in the input parentheses gets evaluated, and then the result is assigned to a variable. So the way the input function is usually set, we have some object that's set equal to input, and inside these parentheses, we can put a prompt message, enter a number. Then the print function you've seen from last time, because we printed hello world. That takes the contents in the parentheses and prints it to standard input-output, which in the case of a Jupyter notebook is a computation cell or is a code cell. It's possible to put multiple expressions in either of them separated by a comma, and we can also build our own functions, which we're going to do later on to handle that. So input as a function here is a bit on the crude side, but it's good to get started with. We'll find better ways to get data into and out of our program. Now a little bit more about strings. So a string has a name, the name of the string, and then depending on how many characters in it, each character is represented as one location in the string. So you can think of a string as a kind of a list. A string is a list, and upon creation it's immutable, meaning it's not easy to change the contents of the list. So here's an example. of a string. I don't know what the name of this string is. Let's call it Fred. So here's a string LIGHT blank RAY. In older computer jargon, the blanks are called white space. So the first element has index 0 is this capital L. The second element, which has index 1, is lowercase I. The third element, index 2, lowercase g. The fourth element, index 3, lowercase h. The fifth element, index 4, is a t. The sixth element, index 5, is the white space. The seventh element, index 6, is the r, and so on. So from beginning to end, the elements count from 0, 1, 2, and so on. We can also go to the end of the string, which is preceded with a minus sign, and so the rightmost element of this string is -1. -2 is one place from the right, -3 is two places from the right, and so on. Strings can be compared, and they can be sliced. Slicing is to take a sequence or a portion of the string from start to end and pull that out of the string. So here's an example of a variable s, which is a string. We're going to take from the string the first 12 elements. We're going to add to that the character stream WO, and then we'll add to that element 12 to the end. So this goes from the beginning to position 12, put WO, and then put 12 onward into a string named S, and then we'll go ahead and print S. So here we're taking this part of the string, slicing it, and we're taking the WO and we're putting it right there, and then rejoining everything. These plus signs are concatenation. So unlike arithmetic, it's not adding things in the same sense. It's taking that first part and joining it to the next part. All right, so this actually concludes the presentation part. It has some examples, but these examples are actually done in the lab. So other than reading them to you, we're going to, in the lab, do a program that'll take two numbers. And, well, it'll do input and do something with it. Then we'll do some more input here. This third one right here is actually a formal lab exercise that you're going to want to complete and turn in. And then some examples in string and indexing. So that completes the introduction, and I'm going to, I'm actually going to see if I can work if I stop and restart a recording. Yeah, I'm going to stop the recording and then restart it. It makes it easier for me to edit the end result. So are there any questions before I stop the lesson recording? Can we do a 5 to 10 minute break here before lab? Tina, absolutely. Everybody leave your stuff logged on and we will come back in 5 minutes. Farhang, same to you. I'm going to just stop the recording.
Sure. Also, Steban wanted to have another look at the charts, if possible.
Charts.
I think with the expressions.
Oh, you mean the? I think I know what he means. Not that one. The one that has all the operators. Those.
Yes. Yes.
Okay. Well, there you go, Stefan. They're also in the Data 8 textbook. And actually, they're also in the lab we're about to do. That chart, I think, was the other one he wanted. Okay, so I'm going to take that 5-minute break. I'm about to turn off the recording. So
Okay, thank you.
Don't talk and do anything important while the recording's turned off.